Yo, right. What's up? Week 92 Halloween stream building my own operating system. Week 92, welcome. Thanks for joining. I'm just gonna adjust my camera, get everything in frame. Yeah, so let me just take a moment to get set up a little bit. I think today's a little bit more of a low energy kind of stream actually. But yeah, today we will be working on the bitmap allocator and kind of wrapping up that work hopefully. Yes, maybe I'll add a bit of a pumpkin to the YouTube title here to kind of signal that we're in Halloween mode. Right, so yeah, bitmap allocator is the topic for today. And, oh, let me get the music going. All right. Pop in for a little bit of a test 0. Oh, one sec, where's my, okay, nice. So we're in business. And what? Yeah, so today, bitmap allocator, I'm gonna work on some unit tests. I'll do a bit of a recap of what I've been working on in the meantime, and then we'll finish up some unit tests, maybe using AI to help us generate those unit tests. Hey, Signad, good evening from India. Right on. Thank you for joining. Hope you're having a nice Sunday evening. Right, so got Twitch booted up. Cool. All right, let me just slowly ease my way into this. The Miro board, a little bit of a roadmap going on. Pop over here for today's work area. 92, November 2nd. What's up, Code Kundan? Cheers. Nice to have you. How are you all doing? You all doing all right today? How was your Sunday? I'm pretty tired. I was at a Halloween party last night and I stayed out kind of late. So yeah, slightly lower energy than usual, but it's all good. We're gonna do a bit of kernel development nonetheless. Pop open the old code. Delete every window, okay. Yeah. Sub Darius. Hey to you also. Okay, so brief recap of what's going on. So first of all, let's just take a moment to check out how the build system looks. Check that out with the single make. I'm able to build both the target and the host, and I got the target's where the kernel lives and the host is where the unit tests live. I can run unit tests like so, and then I can go into the target directory and then make jkemu. Run the OS from scratch. Yeah, pretty much. I think my approach is a little bit unique in that I'm using a lot of third-party libraries. So you can decide whether that counts as from scratch. But it's not like Linux or something. So yeah. Okay, so today what happened to your face, bro? It's Halloween. It's Halloween, bro. Halloween. Day of the Dead. Vampire costume. Yeah, I was like a vampire last night for the Halloween party. No need to be alarmed. No need to be alarmed. Okay, so quick recap on what happened. And so, yeah, I mean, I know not every country celebrates Halloween, so it might have been a bit surprising. I just have extra makeup. That's really just the reason. Bought too much makeup. Okay, so this branch was all about adding kernel lib. Kernel lib's this separate thing from the kernel. It's this basically this library that's designed to be independent from the hardware. And because it's independent from the hardware, we can run it in we can build it into a unit test binary that runs on my host. And so this part of this branch was just all about adding this idea of a kernel lib. And once we have kernel lib, we can add a kernel lib test, which is the test binary. That's what we were just seeing. Then I just did this like tiny little set of fixes, and then this was also not really too important. Okay, whatever. Let's just get to the good stuff. So today we're going to be working on test frame allocator, and the goal is to add unit tests. We only have 2 unit tests, and so now it's time to think, what would the actual unit tests be that I would want to have here? And so the job, so I guess like I'm not completely finalized on a lot of the terminology exactly. For example, I haven't completely decided on the naming of things. But I was just calling it frame allocator to start, because this is responsible for managing physical memory frames, as opposed to virtual memory pages. So that's why I called it frame allocator. And its job is to receive a memory map from the bootloader and then track which frames of physical memory are free or not. Right. It uses a bitmap to do this. Actually, there's a lot of problems here. Well, okay, so one problem is just this. And so in the prototype implementation from a while ago, static bitmap size. So one problem is that, just as a bit of like a hack to get going, I was using a hard-coded bitmap size. And this puts a hard-coded maximum limit on the amount of physical memory that the bitmap allocator can manage, which is not good if you want to have a single kernel binary that you can plop down on a variety of systems with different amounts of physical memory and have it dynamically adapt to manage those. So this is not necessarily amazing. Problem sets hard-coded maximum limit on amount of phys mem that can be managed. And so there are maybe some solutions. Try to make it dynamic, like a dynamic memory map or dynamic bit set. I don't necessarily know if I want to do that right now, although that is fairly interesting. Also, what is up to the other person on the board? Thank you for joining the board. Feel free, yeah, if you're in the chat right now, feel free to join me here on the Miro board if you want. The link is up in the top of this screen. Just go over to the whiteboard link, and you can find the link to this mirror board and just hang out with me on the board. Try to make it dynamic. This is actually kind of an interesting idea, but I'm sort of thinking it might be better to have unit tests first. But the general operation of how this would work, though, so the problem is, our goal with making this frame allocator is to provide the basic ability to dynamically allocate memory on the system. This is the fundamental, basically, thing you need in order to do any kind of dynamic memory allocation. But in order to make this bit set dynamic, we would need to dynamically allocate the bit set, which is a little bit of like a chicken and egg problem, because so how do we dynamically allocate that memory then? And as far as I'm aware, there can be different solutions, but to make it dynamic, so first we need to add an ultra simple, e.g. bit or bump allocator, and we can reserve, e.g. 1 frame just for the dynamic bit set. And so we have like our whole big range of memory. I don't know where I can see. Where's the map? There it is. Okay. We have our whole range of memory, and the idea would just be to just pick like the first usable frame and just sort of pass it and transfer ownership of it to this bump allocator and have it be managed just by this bump allocator. And then the bitmap allocator can use the bump allocator to allocate the bit set. To dynamically allocate the bit set based on the amount of total memory observed in the memory map. Yes. Then the bitmap allocator needs to know to never release that special bit set frame as available, basically. So that just, even though it's technically in the usable region, it will always just need to be marked as reserved somehow. But anyway, that's sort of sketching out what this would look like. But like I said, I think I will not do that immediately. What's up, lonely producer? Hello, hello. I think creating a compiler from scratch is harder. I don't know. They're both hard. they're just different kinds of projects. I don't really know if I would have enough expertise to say necessarily. They're both hard in different ways. Okay, let's go. So, what kind of tests do we want to have here? So, I'm just going to take a moment to kind of sketch this out. So we already have our two existing tests. Basic test, no usable memory, we already did that one. Some usable memory, allocate a page, like running out of memory, observe that the alloc fails. And so what about deallocation tests? I think we do not test deallocation, actually. So that would also be interesting to consider. Let me just quickly read through this code again. So we have a bitmap allocator, and it has two public APIs. It takes in the L memory maps, the memory map, and it allows you to allocate and deallocate from this range. Right, so no usable memory allocation just simply does not succeed. Okay, that's easy. And I'm just going to keep brainstorming a little bit, testing with non-contiguous ranges. Because, for example, in real life, the memory map specifies what physical memory is available, but really we can only use the usable chunks. Yo, what's good, Ismail? Welcome to the stream, the Halloween spooky stream, even though it's technically November 2nd, so we're a little bit late, but I had too much makeup from this Halloween party I went to. So yeah, so we're doing spooky kernel development today. We can only use the usable regions. And so we want to test that our bitmap allocator can support this, yeah, like a memory map that sort of looks like this. Right. Let's just read through the frame allocator quick, just to refresh our memory about how it works. So let's just begin with the constructor. So the L memory map span is basically just like what we're looking at here. It's this container of these structures that has a base length and a type. And the constructor initializes the bit set using the memory map. And in order to do that, we iterate every entry in the memory map. And if it's usable, we initialize a usable region. So our bitmap defaults to everything being not usable. Or like basically like unavailable. And then we selectively initialize ranges of the bitmap based off of the usable regions. And so for every one of these usable regions, we go through and we basically just, okay, what do we do? Basically the way I'm doing it is I'm using this offset, and this is an offset from the base. And I'm hard coding my page size assumption here. But we basically skip through every frame size and we compute the frame number, the physical frame number. And then we mark that as free. And so every frame is represented with 1 bit in the bit set. And so by default, every single frame is marked as whatever the opposite of free is, like used or something, or used, I guess. Meaning it's not available, the bitmap allocator will not give it out. And so there are certain exceptions for the usable ones, and we mark it as free. And to mark it as free, we just set that position as true. And so 0 in the bit set is Not, yeah, 0, wait, let's explain. Defaults to 0. So 0 means used, 1 means free. Right. Okay, so that's a bit of a refresher about how that works. So we basically have this bit set. It's like all zeros except for like a bunch of ones in like certain chunks. And I'm wondering if it would be useful to expose a method for testing which returns how many free frames there are. That sounds useful to me. Let's just do that. Int, what's the name? It's like num free frames. Const definition, add definition. Man, my whatever I have going on is completely broken. That completely did not work. Okay. Get the num free frames. And to do this, we are simply going to we literally iterate. Why? Oh, I need the I guess I do need okay. Const. No. Okay, wait, no. Wait, okay, noob hours. I'm forgetting everything I know about programming. Oh, I'm stupid. Okay, that's why. Okay. Okay. So now, so 0 return rets. And you know, there's probably a better way to do this. There might even be an API here. What functions do we have access to? Count. And it even uses, I don't know, what, SIMD or some stuff like this. And pull out. I would think it would model after this bit set, which is maybe easier to read. Okay, count. Return the number of bits set to true. So that's actually great. It's actually perfect. So return mbitset.count. So now that is like maybe kind of useful because now check it out. In our tests, just to sketch it out, now we can do something like check allocator num free frames equals 0, right? So, okay, 20-second break. Feel free to join me for a quick stand-up. But yeah, so in theory, this is what it looks like. So we build our tests. I mean, just quick check that out. And so I modified the frame allocator, and then it rebuilds the kernel. And I technically didn't need to do. I technically only needed to do the host one there. But so now we're passing. Let's just make this fail to just observe that. I'm gonna make host. And now we see this fails, right? Num-free frames is 0, and we thought it would be 1 in the test. So that's what that kind of looks like. So now we're gonna put this here. 1 bit represents 1 frame, which is basically the same as 1 page, which is 4K. Yep. And so that's sort of the idea here is, the idea is to start building up our ability to dynamically allocate memory on the system. And basically the first part of that is like allocating frame size chunks. Not dynamic, it's like not dynamic size. Like it's like you can only allocate frame size chunks. And then once you have that in place, you can build another layer on top of that can build a memory allocator that can allocate like, you know, more flexible sizes of allocations. And it's just going to call into the actual frame allocator when it needs memory. So in this example, what do we see? So time to just remember how this works. And so we're specifying the base, length, and type here. And so in this case, I'm going to also say that we should have 1, and we can just easily see if I'm right. Test pass, good. So if this was 2, the test would fail, right? So good. So this is 1. So that's, I don't know, it's just like a nice convenience little thing to have. As like just a different kind of consistency check. Okay, and so let's just think about like, yeah, I mean, this is not really the most exciting part of software development, but it's a very important part. Thinking, just at least spending a little bit of time thinking through your testing strategy. What are the kind of edge cases that exist for this code? I mean, we don't have to write tests at all. We could just keep moving forward with plain development, and maybe that'll be more fun. But then we would not have any ability to check if our code works over a long period of time. If I like make a change later, I want to be able to run tests to just do some verification. So anyway, edge cases. So deallocation would be one thing. Testing with non-contiguous ranges, different types of yo, what's up? Shaya Mendra. Yeah, scaring the seg faults. Absolutely. Different types of regions, perhaps. And I mean, we could even go as far as making a really accurate test that actually uses basically this memory map. And I'm just gonna go into the target. See target. And right, so in this thing is kind of printing out a lot of stuff. Oh, okay, the code for printing out the memory map is not here anymore. It maybe got stashed somewhere. Actually don't see it. So. Oh, it's probably in one of the other branches. Quickly checking out the old ref log. Sorry, I was just trying to find. In case where I was doing frame. Okay, whatever. So, what do I do for work? I work in the music technology industry. Yeah. Okay, anyway, that was a bit of a distraction. But we could even go as far as using like a pretty realistic type of memory map. Something that looks a little like this, but okay, let's just keep going. So, so no usable memory, easy. Cannot allocate anything. And then, so let's write a test for, let's like write a basic deallocation test. So in our test, we have just one page. Like what's the simplest, like beyond the no memory case, what's the simplest test we could do? We have one page or one frame available, and we can observe that that it is one frame available on construction. We can then allocate it, observe that we get the base address here. We try to allocate again. We could even go, we could go crazy. We could say, okay, now we have 0. And so now we try to allocate again. We observe that we do not get anything back. We then allocator dot dealloc, which is just a void, or wait, and we need to dealloc the OP adder, which is what we got over here. So now we're going to check that this is 1 again, and and we could even, I don't know, we could even go as far as like just reallocating again and observing that it's back at the same. So this would just be a more full test of like, okay, allocate something, it's the only thing available, cannot allocate after that, we free it back, and then we can allocate one last time. And see that is the same. I wonder if I could host. There we go. So that is working. Okay. All right, now, sorry. Oops, sorry, the old chat GPT. Just in case that's useful. So okay, what could we do now? We could do more variations on this theme. Like we could just have a bit more memory, for example. Yeah, sort of. Like we could do 2 pages. I don't know. We could do several pages. I think maybe the more important aspect. Sorry. More important aspect So let's say we got 8 pages. I think, yeah. So now we're going to check that this is 8. And now, yeah, let's just and maybe there's a way we can be a bit less verbose here. I don't know. Well, we have to get something back. Check if it's valid. Check the value. So we could, we could do this. Is that understandable? Check. I actually don't. I find that a little bit less understandable than the previous version, actually. This version is much clearer to me, that you allocate something and then you check that it doesn't. It's like the value is false. Okay. But over here, so now let's just go a bit more hardcore with it. So let's get 2, 3, 4. So maybe maybe we don't even need that first test if we have this one. We're going to allocate 4, then we're going to just check. So now and it's going to be 2, 3, 4, 5. Okay, but I just thought of another edge case. So let's do a bit of interleaved alloc free behavior. So we're going to allocate 4 things. They all need to succeed. They should have these values. Now we're going to check that there are 4 remaining. And then now let's get a little bit funky with it. So now let's just free like the second one. Okay, so allocator dot dealloc hex to hex 3000, right? I'm going to comment these out. Okay, so now that's going to free the second slot. Let's free the 2 middle ones, but in a certain order. So let's, I don't know, let's just do that. We'll free the second one. We'll then check that there's now 5 available. I just gotta go assassin this here. Reason why I'm not using an arena allocator. So my understanding that arena allocator would kind of build on top of this, on top of the frame allocator. I'm working on just the absolute basic frame allocator right now. But maybe I misunderstood you. So let's say, so we allocate 1, we now have 5 available. If we try to, so now let's allocator.alloc, and then, actually, no, I think I'm being like a little bit, I'm actually, no, what I just realized is so I'm checking that the optionals are valid, and then I'm dereferencing them and checking that they're equal to a number, but I actually don't need to do that because you can just directly compare optionals to values. And if it's not valid, I think it'll just fail the comparison. Let me just test this real quick. I'm pretty sure that's true. So let's just try this. So let's just do it over here. Let's just check that p-adder is equal to hex 4000. So p-adder is going to be a null optional. Wait, yeah. And so this is just going to fail the first test. No usable memory, blah equals, yeah. So right, so that fails. So anyway, so the point being, we can simplify this. So now we just simply allocate a bunch of things. We just check their values. We deallocate. I'm just going to check that this returns 3000 back, right? So we're going to deallocate the 3000. The new frame becomes free. We allocate it again. We get that one same back. We're going to allocate. We're going to deallocate. Let's say we're going to deallocate the 4000 and then the 3000 in this order. We're going to check that now there are 6 available, and then we're going to check that if we allocate another time, we're going to get the 3000 and then the 4000. Memory allocation final boss. That's funny. So what I'm just trying to do here is just sort of run the data structure or the class through just a variety of like just basic operations, you know, allocate, deallocate, check if it's free, do things in kind of like a weird order. So, and like test the ordering. So for example, in this case, I'm doing it specifically in this order because I'm deallocating the 4 and then the 3, but I want to observe that when it's time to allocate again, it goes directly in order because the way we allocate is we just scan the bitmap from start to end. Yeah. Oh shit. Okay. And then, I mean, I just wrote a bunch of code, and it's possible that it doesn't really work even. So let's just this would be a perfect time to run the tests, and they do pass. Okay, good. And so now we're back at 4 left, right? And then now I'm just going to go with the allocator dealloc 4 times. Shit, but now I need to, now I'm just going to deallocate in like a completely random order. 3000, 5000, 4000, 2000, right? And now that I actually think about this, it's sort of interesting. What should happen if we are deallocating a frame that is actually not available? I think we would want to assert this. Is memory aligned? Memory aligned, interesting. What does that mean? Is the memory aligned? So that could be asking if the bitmap is aligned, but actually that doesn't really matter. But as far as the bitmap allocator is concerned, it's always returning frame aligned frames. And so aligned on the hex 1000, like 4K frame size kind of thing. But if you're asking, is your memory aligned? I mean, maybe that's also asking like, at the memory map, like, are you guaranteed that these things are aligned? And that is an interesting question, because even, for example, we see here, this is not aligned. This base is not aligned on the frame size, but it's also not usable. It's also not usable. What I believe, let me pop open the old Limine protocol document. Basically, my understanding is this is specified in the protocol, and exactly, it's right here. So I'm just gonna take a screenshot. All right, quick break, be right back. But yeah, so if we're, I mean, alignment is yeah, it's interesting just to think about that for a quick set. So basically, it's an interesting question. Can we trust that these ranges that we receive from the bootloader are going to be aligned? And based off of this sentence, yes, for both base and length. Usable and bootloader reclaimable, but not the other ones, like not the reserve, not the other ones, but for the ones that we care about, bootloader and usable and bootloader reclaimable, yes, they are guaranteed to be aligned. Good question. Okay, so now we're just back over here, and we'll just finish this up with the old check 8, and let's give that a run. It passes. I'll just sometimes, just to make sure, sometimes you just don't really know if it's actually running your tests, or if you're just running the totally wrong thing and you think it's passing. And so I always like to make it fail. There's a saying, never trust a test you have not seen fail. And I do tend to believe that. So, okay, so I'm just gonna add a bit of a so now the question, do we even need this test anymore? And yeah, so this is done. Observe that I mean, we could do this here even. One thing I don't really love about this test is it's pretty long, like, and it does a lot of different things. I wonder if I could break it up even. And so we initialize it like so. I don't know. There's a few distinct sections, and so maybe we could go on with the info. Alloc pages, dealloc pages, and this is, and also the point of these messages is to help the next programmer understand a little bit what my intention here, just to be a bit more explicit about that, because it's not immediately obvious. Like, my intention here is actually to explicitly test that we get, that even though we freed it in this order, we get the 3 first before the 4 if we go back and allocate. So free frames are allocated in numerical order or something like this. Yeah, something like this. Okay. And so this is sort of several contiguous. And so this is our contiguous example. What's up, Saran? Nice to see you. How are we doing on the, we got 8 people in the chat. Cool, cool. Nice one. No one on Twitch. One person on Twitch? I can't tell. It's hard to tell. Okay. Still haven't cracked the Twitch code. Okay. So that's our contiguous test. And I would even go as like, is it now is the part where we decide, okay, is it even useful to have this simpler test anymore? I mean, the one thing what we're not really doing, we're not testing running out of memory here because I allocated 8. And so I think I'll just keep it around basic 1 page of memory. Okay, good. So deallocation tests, got some of those. Okay, non-contiguous ranges. That's interleaved, alloc, and free. Okay, before I go any further, I am going to actually come back into the production code. So we're allocating the API for allocating is like you just allocate, you don't pass any arguments, you just get something maybe back. And then the idea is that you pass the thing back into the deallocation function to free it. But what if there was some bug in the code where it was not even free in the first place? And you were just deallocating a random thing. That should not happen. So I'm going to go ahead and add an assert. I'm going to assert that is, wait, what is it? Is used, right? Except, okay, so that's going to be here, I guess. Is used frame, no. And so this will just make sure we crash the kernel in case there's a bug where we ever deallocate like a randomly, some like random frame that was never passed out basically. And let's just try to give that a bit of a test run here. So, okay, so, and you know what? I'm also kind of not liking how verbose this allocator, that word is so long to type out. At what? Allocator? But I also don't really have any better ideas. BA, right? Bitmap allocator. I don't know. Maybe we'll try that. I just don't like typing out that long word. But then I don't know. Helper does, maybe it's not that hard. So anyway, we get the BA, and then let's just dealloc some random thing, right? So this is the case where there's a bug in the kernel and it tries to deallocate some random weird thing. We're going to assert and bon appetit. Nice, yummy. And actually this will be interesting to observe because it's going to pass the tests. Wait. Oh wait. Wait. What? Wait. Whoa. What? Okay, so I mixed this up. Free. Okay, used means it's not available to be given out. Free. Okay, that's a little bit confused. So is free. That's what I meant to put here. Ifs. Free means free to be given out, and in fact, wait a sec, no. Everything is 0. I initialize things to free. I give them out, which marks them as 0. Wait, so is it even possible? And so, okay, so wait, actually, I don't know if it's possible to do this assertion. Oh, what the, I got some makeup on my hands. I don't even know if it's possible to do this assertion, actually. Wait a sec. The assertion, yeah, wait a sec. So, this is our bitmap. And then we initialize like 2, based on the memory map, we initialize 2 free frames. We give the first one out, so it looks like this. And then later on, when you go and deallocate the memory, you pass in this thing, and we want to return it back to this state. We're just flipping things back from 0 to 1. So the assertion is actually that it's not free, right? When we're deallocating, we want to be transitioning things from the 0 to the 1 state only. That thing needs to be a 0. So we're asserting that it's, wait, but I was right. Wait, I feel like this should be so much simpler. Okay. I want to assert that this thing is used, right? Like, we mark it as used, right? That's what our bitmap allocator does. We mark it as used, which means set it to 0. So now when we come back into this function, it should be 0. So I am not understanding what happened. Oh, wait a sec. Oh, because, okay, whoa. I get it. It's because here, everything was just used. We never, wait. Yeah, in this example, there's no usable memory. Okay, so the test case that I'm interested in, okay, sorry, usable, let's go back, like let's hex 2000, the classic 2000, 1000 example. Okay, so dealloc can always be called to like free a random block, and technically we could assert that that block is in the range, is in a usable range, and it's not some random range, but that's like a kind of expensive check. That's like a linear scan of the bitmap, unless we do it smarter somehow. So that's like a slightly more expensive check. But the cheaper check is just something like you alloc, let's just say we alloc, and then we're gonna get the 1000. But then let's say we're gonna dealloc some other, in this case, what we're testing is deallocating the not yet allocated one. Okay, so we do not allocate. We simply try to deallocate something that was never given out by the memory allocator, which is this. We have the 1000. We have this thing. No, is that 2000? Is that 2000? The memory allocator never gave it out, and the code tries to deallocate it. That should be an error. And if I got it right, we failed the tests. Good. Real quick, just to show off a little bit, because this is actually kind of cool. So assertion, this is making use of my new kind of decoupled assertion handling infrastructure, because in the normal kernel, when an assertion fails, it just infinite loops and spins and like panics, like it just spins forever. But in my unit tests, I don't want to just spin forever. I want to fail the unit tests. And so the way I've done this is that the kernel and the kernel unit and the kernel lib test each define their own assert.cpp file. And that exists in the kernel, and that exists in the kernel lib. And in the unit tests, we can implement what we want to happen in response to an assertion failure. And in this case, I am doing like a normal like std abort, which is like something like a thing you might do to abort your program in user space programming. So. Okay, so that clears that up a little bit. So maybe let me do, could consider asserting if pattern does not correspond to a usable memory region, but that would require checking against the memory map, which is maybe more expensive than we want to do on every dealloc. Something like this. Yeah, I mean, assertions, don't really use assertions enough when I code, might get more into this habit. I didn't either for like my entire programming life until I started working at a company that used them a lot, and it turns out it's really helpful at finding bugs and making it easier to track down bugs closer to the source. I think people probably have different opinions about this, but I think they're good. I think it helps with, it makes things more likely to crash in your unit tests. And if you're fuzzing your code, if you have assertions generously in there, yeah. But the thing is, like, you don't need to, like, the kernel completely runs if you don't think to do this, but you just might end up with bugs that you just don't find or are very hard to debug because something goes wrong, but it's not detected until like way later in execution. And if you simply had an assertion, you could just check that easily. So got the but the thing is, now my unit tests simply always fail. So I actually don't know if I can. I mean, I can't just leave it like this. Like I can't really test this that well currently, actually. Like, I can't test it that well because it just crashes the tests. It fails the tests. I want it to somehow pass the tests. Like, the way I've seen this done is there's just some mechanism where you make it actually throw in like an exception or something. And then the test case can try to do the thing and then observe that an exception was thrown. I don't know, maybe that'll be fun to try. How would I even do this? So what would this... wait, no. I would want something... I don't want to change the code here, but I just want it that when we're running the unit tests, these things get... converted. I totally could actually. Wait a sec. Wait, instead of, wait, no. Assert that. Instead of aborting, I could throw assert failed. I don't know. This is like this is not really the way you're supposed to do it. But I do have full-on assertions in the unit tests because I have a full-on normal environment. So I don't know. What? So now, like, this actually, it no longer does the sig abort thing. Now the test fails because it threw an exception, and I can catch the exception. What do I do with this? Can I... I wanted to check that an exception happened, basically, right? And I want to fail it if it does not happen, right? So how would that look here? Try. Okay, dumb question, but is there an else in C++ try? I don't even know. Can you? Is there an else case where in case the exception? I think this is only a Python. I don't actually use exceptions that much, so I'm not really that familiar with them. In case no exception was thrown. No, that's like only a Python thing, right? Okay, so right, and so I guess the flag thing did throw false, and I'm gonna so the strategy is check did throw, right? And here I'll just do did throw equals true. Can't you check both inside the try and the catch? Wait a second. Oh, wait, yeah. So I see. You're saying, but I think maybe, wait, I think your idea is probably better, actually. Wait, because no, wait, I want to make sure that it got here, right? So this, you know, this work, it should never get here. It should always get here, but I just don't know how I would check that it got here. So that's sort of what this flag is for, I think. So yeah. Okay, and now this is, it did not pass because this thing is catching stood exceptions, and I think I threw a string, like I threw a stood string or something like that. Can you use auto? No, I don't think so. And this is purely just out of curiosity, but what type of exception is this? If you just throw the like a string, right? Exactly. So you can catch the const star. Okay, I'm gonna not do that. I'm gonna try to be a bit better than that. I think I'll go with the runtime error maybe. And then now we should check it out that the assertion, unfortunately it prints out assertion failed, because that's, I mean, I don't have to have this here actually. And this is actually kind of interesting. This is like kind of cool actually. So now we can actually test that deallocating a free page. Wait. Yeah. Deallocating like a free page asserts. So this is quite interesting. I'll just maybe capitalize this. Or even, wait, I have this, yeah, wait a second. I have this like full on nicely formatted string right here. I could, could put that into the runtime error potentially. It doesn't matter because over here we're not checking, we're not parsing the string or something. But let's just watch what happens if let's say I just didn't catch the exception. Now our tests fail and we get this like big text here. Yeah, so that, I don't know, that could be interesting. Yeah, I don't know, kind of cool, I guess. So now you can imagine if when the kernel's like all big and stuff and has all these unit tests, and then I break something in the kernel that causes an exception, an assertion to fail, then I run the test, it's going to bubble up an exception all the way to the top and like kill the whole thing. So I don't know, that's kind of, feels like kind of cool to me. So I don't know. This pattern of the did throw is like a little bit unfortunate. Wait a sec. I'm being stupid. I'm using this whole ass like C++ catch2 library. Please replace this with the catch2 way of doing this. So technically that thing works, but catch already includes like all this stuff for doing exactly this thing, because it's like a production library. And so it has like a check throws. What am I doing? So we can just simply say check throws. In the same way you just check things, you can do the check throws. So man, okay, that was a little bit embarrassing. So now let's just see that fail, because you can never trust a test. Let's not assert. Okay. And so we're not going to do the assertion anymore. And so, yeah. So now this test should fail. Failed because no exception was thrown when one was expected. Word, okay. So, assert if dealloc a free frame. I still somehow find this terminology a little bit confusing, like free and used. Yeah. Free ones, it's like kind of like from the perspective of the allocator, there's these pages that are free, and the used ones are ones that are not given out. The free ones are ones that can be given out. And from the client perspective, we're also deallocating used frames. Maybe I can call things a bit differently, like available. I don't know, whatever. So anyway, that's kind of cool. So now we have our assertion here, and we're even testing it, which is kind of nice. Moving on. Okay, actually no, never mind. Time for a palm tree break. Be right back. Okay. Non-contiguous regions. Let's try that out. So I'm just going to copy this thing over. Several non. And so this just gets into also using different types. And so let's just do some tests where we do a bit of interleaving. So maybe we'll do a chunk of 4. We will do a chunk of reserved memory. And this could be anywhere. I mean, it just needs to not overlap. Could that be a 12 or something? We could do a chunk of 1, another, but then this needs to be at you know, I'm just putting 2s everywhere. 2 x 12, 22, and then we can just, I don't know. Maybe we just make this 2, just to keep things a little bit simpler. Then we go for another set of 2. Put this at 4. So now let's just run through some tests. And so got the allocator. Or would it be so bad to call this thing alloc? Would that be the worst thing in the world? Alloc.alloc. This is real bike shedding territory. How to name things. BMP. Maybe. Yeah, I don't know. Sort of like, it's like this trade-off between how verbose you want to be and how concise you want to be. I don't know. I'll just keep it like this. So in here in this case, we have 5 frames. We got 2, 1, 2. And so let's just kind of check if that works. Okay. So now we want to allocate across the gap, basically. And so now we're going to allocate, let's just do 3, I guess. And we're going to get, I mean, let's just do all of them. Right. 5. Okay. And it's going to be 2 and 3, and then hex 22, and then hex 42, no, 42, and then 43. Let's just run that quick. And let's just see it fail, just because it's always good to see your tests fail. Good. Okay. So now we allocated across both of these gaps. Now, yeah, let's just check that. It should be 0. Good. Okay. I guess let's try to free things. Is there any kind of interesting order? I don't know. More or less like a random order, I guess, probably some kind of random-ish order. So I'll do 42, 22, 3. So now we should have 3 frames available. Let's just run that quick. Okay, good. And now, yep. And now we just kind of go in one more time. I'm doing just another 2 allocations and just confirm that they're 3 and 22. And I think that's probably good. You know, and so that is going to leave us, so we had 3, that's going to leave us with 1 frame left. Let's just run it through. Okay, cool. And just, you know, make sure it's really running it. And check it out now. And we get some messages. I don't know how useful those are, but I don't know, whatever. So there we go. And those are our tests. So maybe a little bit of overkill to do like all this testing for what's kind of simple, but I don't know. I think it's good practice. In the future, I mean, I didn't really use AI this time. But I don't know, in the future, that could be nice. Okay, so we got our tests, so that's cool. I'm gonna come back over here and amend everything in this commit. So this is our commit, and this is sort of what the commit looks like. It's like the code, the production code is not like totally polished, but we add our production code, which is the header and the source file, and then it's accompanied by some tests. And actually, I mean, this thing is actually a separate commit. So, oops. Wow. Let me see. Okay. So this, okay, so let me just, how do I, wait, what? Okay, yeah, okay, so I want to actually, oh wait, no, I accidentally amended everything. So I want to split this thing out actually. So this thing needs to come out into its own commit, and this commit is throw exception if assert fails in unit tests. This allows us to catch it and test that assertions should be thrown in that certain cases should assert, basically. All right. What's up, some Twitch people? Injust and 16. Hello. What's up, Buffer? Nice, 11 people in the chat. That's cool. Okay, so we got make file cleanup, this kind of random thing for not actually aborting, but throwing an exception, which was useful in this one case. I'm just thinking if there's any other, is there any reason not to do that? Not sure. What's up, 16? Question. How do you test the kernel? That's such a good question. It's literally what we are working on right in this moment. So just to preface things, I'm still sort of at the beginning of like this journey of making the kernel. And so my approach for testing is to have unit tests. I'm designing the kernel such that parts of the kernel that do not have any direct connection to the hardware, and they're just basically just like generic data structures and algorithms, can be separated into a separate library, which can then be compiled into like a test binary that runs on my developer machine, and I can write unit tests against these generic data structures. And that's literally what we've just been doing like this whole time, just like kind of working through our first set of unit tests. Yeah, and I don't know, this is something I mean, I haven't read like that many hobby kernels, but as far as I know, a lot of people don't go through the effort of setting up this infrastructure, and they just do everything in the kernel. And this sort of makes it difficult, and it kind of prevents you from doing unit testing and isolated testing like this. So that's sort of my strategy. I could also imagine us doing kind of a different form of testing where we actually boot the kernel and just confirm that it boots. And so that's not a unit test. That's more like an integration test. And that's more from like the high level perspective, looking at the system as a black box. It would involve like running the QEMU command line and then just like checking the serial console output or something like that. Buffer asks, TDD works for OS dev. I would say yes, absolutely. I would say yes, absolutely. In general, my opinion is that while there are some things about OS dev that make it different from like normal development, there are a lot of parts of it that are like not really that special. And a lot of the normal things you would just do in software engineering and writing programs apply just the same. What's up, Akosh? I'm gonna hit you with the resources page, and the advice that I give everyone is just to follow an online course, like a free online course from a university, which is what I personally did and like worked for me. Yeah. All right. So okay. So now this is the commit, and this is the commit that basically just like adds the code. And the tests. And so what I just like about it is it's really nice to see a commit that has tests in the same commit, because that helps you have a bit of confidence that the code actually works if the tests pass. And so it's always just nice to, anytime you change code, it is always nice to try to add some tests in that. Oh, we got the YouTube versus Twitch, YouTube versus Twitch flame war. Yeah, YouTube chat is getting spoiled. All right, see you later, 16. Thank you for joining the Twitch chat. My first person ever to join the Twitch chat. Okay. So I think, yeah, so here's the part where I'm going to actually try to like finalize the code. And I just have this drop me commit. So this commit is not going to actually be merged in this branch, but it's just a little bit of code in the kernel that just actually exercises this thing. Here's a fun experiment we can try. So now we can actually try to, and my fuzzy lines are all over the place because my compile commands.json file is pointing at the one for the unit tests, and it's not where it's like a little bit annoying. If I compile, yeah, like I need to figure out a better way to solve this, but the way it works is I point the IDE at, wait, that actually doesn't make any sense. It was actually pointing at the host, not at the target, which is what we are looking at here. So workspace? Straight up, I don't. Yeah, I think this is, so I think this is actually the one. And so now I'm going to point it at the other compile commands for the target, and then all the fuzzy lines go away. So it's kind of nice. It's kind of annoying switching these. I don't know. Maybe there's some solution for that. Anyway, back to over here. So what I want to do is I want to observe that assertion fail. And so I'm just running the kernel. We have our basic test where we are allocating a lot of stuff. And what I want to do, I want to test that alloc.d alloc, and it's time to, I mean, even 1000 would do it. Wait, no, it needs to be a free frame, and so it needs to be 52,000. Right, 52,000. So that would be, that's the first actually usable frame. The bitmap allocator never gave it out to anybody, yet we have some random client trying to deallocate that frame. So that's bad. That's a bug. And let's see if we can just observe this bug. Assertion failed. Frame allocator dealloc 32 is used. Cool. What's up, hello code? I'm good. How are you? So it worked. And right now I'm just sort of thinking, so let's say I was making the kernel and then I saw this. How do you debug this? Because really the problem is sort of here. And so let's just say I'll run this in the debugger and LLDB. Wait, no, I gotta go into the target. Continue. Okay, so now the kernel is spinning and I just Control-C it. Now I can get the backtrace and I can be like, okay, man, what is going on in the kernel that is causing that assertion failure? And I can then see that, okay, dealloc, like let's just go up, 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 bam, okay, interesting. But like, okay, so like who called the dealloc? We'll go up one more time, bam. Now here's where we can see the code that triggered the assertion, and we can start to wonder why it's doing this. So that's just sort of me like cosplaying my future self when I need to debug why things fail. So that was cool. Debugging, yes. Yes, sir. Okay. So basically we're in the final stages of like basically being ready to land this branch, basically. And it's just like kind of not ready yet. The few things that are not ready, it's just the small details. Okay, so details around naming, around, I don't know. Yeah. So for like, is frame allocator the name I want? Or should I call it bitmap allocator just directly? I mean, it's like kind of confusing that these things are named differently. Frame allocator. So I'm gonna say I don't. I think this name is all right. I mean, it's the specific like implementation of this kind of allocator, so that does make sense. So bitmap fizz physical allocator. Other OS projects might call this the physical memory manager, but this is really one implementation. This is really the bitmap physical allocator. So bitmap phys or bitmap frame allocator maybe. So to me, what's important here is to name it in a way that it's clear, okay, this is using the bitmap. This is like specifically the bitmap strategy for doing this. And also that it's the physical memory. So it's like the physical frame allocator. I'm gonna kill the prompt because I'm gonna get going kind of soon. So this is a little bit wordy, but let's just go with it. Bitmap frame allocator. Rename the file to bitmap frame allocator. Rename this file to bitmap frame allocator. Rename the includes bitmap frame allocator frame. Just do a big old grep. And I don't know why my git is okay. Kernel is no longer doing its thing. CMake lists, need to update that. Test the test file. Rename bitmap frame allocator. Include bitmap. Let's get this new line out of there. I think I'll just move this to the top actually. Okay, got the catch include, got the one for this file, got the third party one, and I got the standard library one. Okay, how is our build doing? Do we build anymore? Nope. Do we build? Yes. Okay. Nice. So conflicts. Okay. Change. Let's go with this. Okay. So now it's looking a little bit. We did our bike shedding. Picked a name. Looking good. Now let's look at the code. So how's this code doing? So got the class. Got these things. What is next now? Good question. So there's a couple options. So one option is to look into this thing. And so this is like the hard-coded bitmap size. And this has always been kind of a hack just to like get going, but because if there's a hard-coded size here, that just is a fixed hard-coded maximum limit on the amount of memory that can be supported by the OS. So If we wanted to get kind of fancy, we could try to make that a dynamic bitmap. And I was kind of drafting this out earlier on the stream. It would, we would need to add another allocator even before the bitmap allocator, which would be like a simple bump allocator probably. And then that is used only to dynamically allocate the bit set rather than having the static hard-coded size. And then the actual bit set would need to like change. I don't know if frig bit set would work anymore. I think I might need to like, yeah, write one or copy code from frig or something. So that would just be kind of, that would like sort of be kind of convenient. I mean, not even for me. I don't really care about running this on different machines with different amounts of memory, but it would just be a bit more sophisticated, robust, flexible, I guess, rather than just like this hard-coded size. But honestly, there's also not really a lot of problems with the hard-coded size too. And it's sort of a question about what is most interesting. Really, the goal here is once we have this, we can start working on virtual memory, because then now we can use the bitmap allocator to allocate page tables, which yeah, which would be nice, because the general high level like goal would be to get the kernel into I don't know, it's like production virtual memory setup and kind of out of this bootloader setup. So I think we had this discussion about this in a couple weeks ago. NSG was here, and right, so the discussion was about it was basically just here. It's basically just like, you don't really want to be using the initial page tables in the bootloader reclaimable region, because then you can't just easily reclaim all of that memory in that region. You would need to be kind of careful about what particular things are like still in use. And so I think there's this idea of like a migration step where the page tables need to be migrated out of that sort of like temporary-ish bootloader reclaimable memory and then migrated into the actual usable, like normal memory region, at which point you can reclaim the memory. So that's sort of the vibe, I think. And so, yeah, something like that. So right now we're just using this kind of random number, which is based off of this. Honestly, does not really matter. So I'm happy to leave it like this for now. So. But, okay, so now we get into the actual code. There's a bunch of random stuff I did that I don't love here. So, magic number 12, to do don't use raw 12. So, what kind of, what should I do? I should make some variables for this probably. Maybe some constant variables. Maybe that goes in a header. Call this x 86 constants or something like that. Yo, what's up, Vpool? Happy Halloween. Did you get into a fight with a C compiler? Absolutely. That's like my daily life, fights with C compilers. Okay, so I don't know. We're just gonna do some const expr inline const expr auto k page size equals 96. Frame size, okay, page size. Frames. Okay. And what? Then it's page bits 12. Oops. Right. Maybe this is confusing. It's just easier to just call everything page. So page bits, right? And so I don't know. And so, yeah, so then we can just start to use these in a few places where it might be useful, such as here. And so I'm going to go ahead and include the x86 constants. And now I can just use k page bits, right? 12. So k page bits. Could have done a find and replace, but there was only 3. Then k page size, right? Times 6. Hey, what's up, Rizzler? What's up? 2x is serious. Yeah, no, it's good. Thank you. Yeah, it's kind of makeup's kind of. I don't know. I'm kind of digging the makeup actually. Yeah, I should wear this more often. Okay, so we're kind of working our way through these to-dos. Pretty much the last thing is just to do assert alignment. Let me just do a quick build just to make sure we're building still, and we're not building because, okay, I messed up the merge. Okay. This thing goes into here. Okay. Yo, what's up, Varun? I see you live streaming every week. Makes me want to grind hard. Thanks for that, bro. Yeah, no problem. No problem. Yeah, do your grinding. Whatever it is you're trying to grind on, definitely grind it out. Okay, assert alignment. What could I have meant by this comment? So, init usable region. So this is like asserting, I guess, that the we can assert a bunch of shit. We can assert that the type equals usable. We can assert right, and then here's the part where it's like we assert that the base mod k page size equals 0. Something like that. Maybe like a little math HPP could be a little duplicate. Math HPP. Inline bool is aligned, and we'll take like let's type name t input and int alignment and return input mod alignment equals 0. Here's the part where we could even have some unit tests for our isAlign function. Test, create, test math. Let's get it. Let's just knock it out while we're here. I mean, I don't even know if I did this right. I just typed it out, but is aligned. All right, we're gonna do a check. Is aligned. All right, is the number 16 4 byte aligned? All right, why is the allocator test failing? Wait, what? Okay, maybe one step. I'm gonna go back here. What happened there? Wait, what? 62. Oh wait, no, I just left it in the broken state, I think. So 3 frames left. We allocated 2, there should be 1 frame left. Word, okay. And then we're just gonna go over to the CMake. We're gonna pop over, add the test math, and see if I know how to code. So now let's break it. So yeah, wait, 15 4-byte alignment. Is 15 4-byte aligned? I don't think so. So cool. So that's just sort of what I'm talking about. Like, here's the part where I feel like it's kind of paying off having this whole ability to just write unit tests, because imagine if I it's just so easy to like write some code, but like I don't know how this works. I don't know if I did this right, and so I'm just gonna write some tests to make sure I did it right. Otherwise, I would need to like put that in the actual kernel and just like run the kernel just to make sure that my isAlign function, that I wasn't being stupid when I was writing it. So so we're gonna do check not isAlign. We're gonna do check isAligned, and we're gonna do some big numbers because that's what we care about. So we care a lot about page size, alignment in the kernel, and so we're gonna be checking stuff like this. You know, not really the most advanced stuff, but hey, it's cool. We have some tests, and so this is cool because it will also be a separate commit. We just get our this stuff, add math.hpp. This can go like, oh damn, okay, never mind. So wait, okay. Merge conflicts happen, okay, whatever, not really that important. What's important, I'll just do that later. What we were actually trying to do is come back into here and now just do something a bit more readable like this, right? So assert is aligned, and then we just gotta come over here and get the the math.hpp. And that sort of passes. Maybe I can make the assertion fail by messing up the production code. Check it out. Now the tests, like all sorts of stuff starts to fail because I messed up the assertion. Cool. So now I've fixed the assertion, it comes back. And I just love how I don't have to run the kernel. I'm not running the kernel at all here. I'm just running these, I'm testing the kernel. I'm testing the kernel's code, but I'm not running Kimu and stuff like this. I'm just testing it in this like nice little unit test. And so we've got our alignment assertion. And is the length also? Time to check that screenshot. For both base and length. So let's hold them to it. I'm gonna hold the docs to it with these assertions. Okay, cool. Because in the code we legitimately depend on these things being true because we're bumping at k page size and marking things in the bitmap allocator. So we really are depending on this, and so it's just nice to really encode that deeply into the code right here. And yeah, I think that except it doesn't compile because of, okay. Right, I kind of messed up the merge earlier. Okay, we're building both the kernel and the tests. Our tests pass. It's a good day, and I'm going to end this stream here. Thanks a lot for tuning in. I'm going to hit you with the Discord. How many people do we have in the stream right now? 15 people. Nice. Thank you very much for being in the stream. And if you're watching this right now and digging what's going on, please subscribe to my YouTube channel. I would appreciate that a lot. Easiest way to support me. Just hit that button. And yeah, I'll be back next week and we'll keep it going. And yeah, I don't know, maybe that virtual memory topic. I think, yeah, maybe that migration of the page tables, that sounds kind of nice. So cool. Like and subscribe. All right, have a nice week and I'll see you next week. Peace.